Back, everybody. First, thanks to the first three speakers. Unfortunately for all of you, I will also be speaking about EventBridge. So that's, I guess, the main theme of today. We didn't align anything, it's just a coincidence. Or it's just the service that you want to use these days. So, my name is Luc van Donkersgoed, and today I will talk about user-driven composable infrastructure with the CDK. And that's an advanced CDK use case that we use at PostNL. So today's talk will be broken down into 4 parts. First, we'll talk about abstraction using the CDK. Then we'll go beyond level 1, level 2, and level 3 constructs and introduce level 4 sub-assemblies. Then we'll talk about how and why we used level 4 sub-assemblies to create composable infrastructure. And finally, we'll do an implementation deep dive and show you how we build the sub-assemblies. So let's start with the basics. What is the CDK? Well, first of all, it's a CloudFormation generator. You define your application, your infrastructure in the language of your choice. You run a CDK synth, and it will generate your CloudFormation templates for you. Next, it's also a deployment toolchain. So you can use commands like CDK synth, CDK diff, CDK bootstrap, CDK deploy to help you deploy your AWS templates into your AWS accounts. But most importantly, the CDK is an abstraction framework. And we use the CDK to abstract things like a secure bucket or an ingestion pipeline, the data analysis module, or maybe your GraphQL backend. And the tools we use to build these abstractions are called constructs. So we have level 1 constructs, which are programmatic abstractions of CloudFormation resources. We have level 2 constructs, which provide a thin abstraction around level 1 constructs, providing sensible defaults and convenience methods like IAM grants. And finally, we have L3 patterns, which combine multiple level 1 and level 2 constructs into reusable building blocks or conceptual modules. And then we use these level 1, level 2, and level 3 constructs to build our applications. And the applications are generally stored as a single project in Git. And the most common ways we use the CDK are either for local deployment. So you have your application on your local machine, you run a CDK deploy, and it's being deployed into your AWS account. Or pipeline deployment, where a pipeline like GitLab or GitHub Actions or Jenkins or CodePipeline detects a change in your source code, checks out your project, and runs a CDK deploy for you. And today I want to introduce a new pattern and a new deployment method, and those are level 4 sub-assemblies. And a sub-assembly is a standalone CDK project that can and will be deployed as a standalone stack. But contrary to common CDK projects, it will not deliver full functionality by itself. Instead, it will integrate with another core module and use shared resources in that core module to provide the full functionality. And the core module is its own CDK project and lives in its own CloudFormation stack. Now, I think many of you are engineers, and you're probably just itching to know how did you build these L4 sub-assemblies and how can I use them. But before we dive into the how, I want to quickly talk about why we built them. So my team at PostNL is responsible for building the central event broker. And this is based on EventBridge. And the PostNL event broker allows applications in our logistics landscape to send their events to a central location and consumers to subscribe to those events and send them to the targets where they want to receive them. And this is really an essential component in our distributed and decoupled landscape. And one of the core tenets of the event broker is that it should allow the applications using the event broker to innovate faster. And we aim to achieve this through self-service. So our producers should be able to independently register new events. Consumers should be able to discover which events are available on the event broker. And consumers should be able to subscribe to those events and send them to the endpoints of choice. And they should be able to do this frequently. It shouldn't matter if an army of baboons is constantly registering new producers or registering new subscribers. We should be able to keep up at any rate. And this means that our landscape is constantly changing. Producers come and go, consumers come and go, but the number of events only increases over time. And although self-service is the main goal, we do need to set some boundaries and some guardrails on those events. And we need to do that to guarantee reliability. And reliability means that events should always be delivered to their consumers, but it also means that events should always match their schema or their definition, which is something that we discussed in earlier talks as well. And one of the ways we guarantee that events match their schema is by putting an API gateway in front of EventBridge. And the API gateway has some methods and resources and a request validator. And the request validator will check any inbound event. And if the event matches the defined schema, it is allowed onto EventBridge. If the event doesn't match, it is rejected and returned to the producer. And that way we can guarantee that the consumers will always only receive events that match the schemas as defined by the producer. And that means that every time that a producer registers a new event, and that happens a lot, we need to deploy a set of components. And then we need to deploy them in our AWS account as part of our event broker pipeline. Now, another important event broker philosophy, or at least the PostNL, is that we want to meet developers where they are. Because we really want to achieve high adoption and a fast pace of innovation. And we can only do that if we meet those developers where they are. So if a producer wants to send their events to the event broker over HTTPS, we need to deploy the ingress HTTPS components. If they want to deploy or send their events to us over SQS, we need to deploy the SQS ingress components. And all of this needs to happen without human intervention. And that's why we need the L4 sub-assemblies to deploy the components per producer. So why do we call these L4 sub-assemblies and not simply L3 patterns? Because they do seem to have a lot in common. Well, an L3 pattern is a part of a standalone application. With L3 patterns, you build your application. But L4 patterns are an application. They are a CDK stack. But they're not like a full CDK application because they do not provide full functionality on their own. They need to interact with a shared core module. And the core module has its own lifecycle and its own deployment mechanism. And that's how we get to the model shown on this slide, where the ingress subassembly contains the components per producer, and it integrates with the shared core module. Now, before we dive into the technical details, let me show you what that looks like in our production environment. We have a number of CloudFormation stacks, and each of these are a deployed L4 subassembly. And each of these stacks simply has a small number of resources, in this case, those required for event ingestion through API Gateway. So now we know what to build. Let's take a look at how we build this. This diagram shows an overview of the deployment process of an L4 subassembly. It starts with a user registering an event in our UI. This is sent to an API gateway, which authorizes the user. Then after authorization, it is sent to a Lambda function, which performs any business logic. Like, is this a valid event? Does this match all our definitions? Is this not a duplicate or whatever? And when the Lambda function has validated the business logic and the business rules, we send a message over an SQS, to an SQS queue to the deploy service. The SQS queue triggers a state machine, and the state machine triggers a CodeBuild container, and that triggers the CDK. And in the rest of this talk, we'll really focus on the deploy service and the details of that component. So let's start with the CDK project. As described before, the project is an abstraction of the resources required per producer. But to deploy those components, it needs to know two things. First, what is being deployed, and this matches the configuration specified by the producer. And the configuration is different per deployed subassembly because, well, we have different producers, different events, they're all configured differently, and that is specified in the configuration. Next, it also needs to know where to deploy this subassembly, and that is defined in the context. And the context will be the same for every deployed subassembly. So, for example, the same API gateway, the same AWS account, and so on. Now, the what part is supplied to the L4 subassembly as a configuration file in JSON, while the where part is supplied to the project as environment variables, which are being read out by the CDK project. So let's take a deeper look at that configuration JSON. It contains all the details of the event as defined by the producer, such as the application name, the name of the event, the version of the event, and very importantly, the schema of the event. So the exact definition of what this event looks like. And then all the way at the bottom, this configuration also contains the ingress type. So in this example, it's HTTPS, but it might also be SQS. And the context is just a collection of environment variables. And they define what the subassembly should interface with. And in this simplified example, we simply included an API gateway ID, which is, of course, well, the identifier of the API gateway we're integrating with, and the name of the environment we're deploying the subassembly in. And with that, we finally arrived at the CDK. So I hope you can all read this, but this is app.py. In our case, we use Python. This is the main entry point of your application. And in app.py, we start by loading the configuration, the producer configuration, from a file from disk. And we use the model from file function here. And it simply reads the JSON file, converts it into a dictionary. Then we call the model from dict function, and that turns the JSON, the dictionary that we just loaded from disk, into a model, which is a Python object. And in the middle section here, you can see we actually return a subclass of the model. So if the ingress type is HTTPS, we return the HTTPS producer model. If it's SQS, we return the SQS producer model. And this model can be used throughout the rest of the CDK project to read the configuration files supplied to it. Then going back to to app.py, so the main entry point, we also load the context, and we simply create one new object, the base system context. And as you can see here at the bottom, all that really does is load environment variables, provide sensible defaults, and supply them as attributes of this object. And then finally, again in app.py, so we're still in the main entry point, we create the CDK stack. And this is really a lot like you would create any stack in any CDK project, with a main difference that we dynamically set the stack name. And we need to dynamically set the stack name because if you don't, every stack would get the same name and we wouldn't be able to deploy this stack multiple times. So we need to provide a dynamic stack name to deploy this project with different names so that all the producer events and all the L4 sub-assemblies can be deployed in the same account. And then in the bottom section, you can see we also override some IAM roles, but this will later be used by CodeBuild. So in the previous slide, in app.py, we created the stack. This is the actual definition of that stack. It doesn't do very much. All it really does is take the configuration model that we just sent and use a mapping to define which L3 pattern to deploy. And the L3 pattern is decided which one to deploy based on the ingress type. So either HTTPS or SQS. If it's HTTPS, we deploy the HTTPS producer construct. If it's SQS, we deploy the SQS producer construct. And this is that actual L3 pattern. So this is the part of the code that contains the actual resources. And as you can see here, we start by loading the context again. So this is, well, the things that we want to integrate with. And then in this part, you can see we actually import an existing API gateway and reference it through the configuration files that are supplied to it. And on the right-hand side, you can see the actual components being configured. So we have an API gateway model, an API gateway request validator. And here in the middle, you can see that the request validator is again configured from the values, so the data event schema that we saw way back in the JSON file, on this request validator and API gateway model. And this then, in the end, results in the actual AWS resources being deployed in CloudFormation. So let's quickly recap what the CDK does. First, it collects the configuration values and the context through environment variables. Then it creates a stack with a dynamic name based on those values. It selects the right L3 pattern based on the ingress type. And then finally, it deploys the resources in that L3 pattern and configures them as defined by the context and configuration. Now to the CDK project, the configuration and the context are just a file in a predefined location and just an environment variable in the operating system. So by providing those two things on my local machine, I can actually start a local deployment. Just do a CDK deploy, and you can see the resources being created from my local machine, and you can see the entire process finishing in about 30 seconds. But of course, developing or deploying from my local machine isn't very user-driven. It doesn't help the actual producer. So instead, we need some sort of a component that can do this deployment, but can be triggered by a user action. And AWS CodeBuild is the best tool for this job, because AWS CodeBuild is simply a container that can execute a predefined script and can be triggered by a user interaction, such as a producer registering an event. So in our deployment diagram, we're still on the lower right. And in the previous section, we discussed the CDK project. And in the next section, we'll look at how to deploy that CDK project. Now, the CodeBuild containers responsibilities are defined in a build spec. And a build spec isn't really much more than just a bash script that defines which steps that the CodeBuild container should take. And we can see it has three main responsibilities. First, it fetches the producer components, and this is really just a zip file of the CDK project that we just saw. And it's stored in an artifact store in S3, and it's copied to the CodeBuild container and then unzipped. Next, we'll fetch the configuration file, so the JSON, and put it in its right place, which is config/deploy.json. And then finally, we just run a CDK deploy. Now, in the previous slide, we saw the configuration JSON being put in the right place, but we also need to supply the context. As I said, those are just environment variables, and here you see the actual list of environment variables supplied to the CodeBuild container. And as the environment variables are available to CodeBuild, they are also available to the CDK project. And now with these two things in place, we just run a code build deploy, or we trigger the code build container, and you can see all the resources being deployed. And again, this takes about 27 seconds. So now the code build container can deploy our subassembly. But the user, all the way on the left of this diagram, still doesn't have a way to trigger this actual code build deployment. So in the next few slides, we'll cover how to do that. Now, as you can see on this slide, the management service and the management UI, the management service and the deploy service are itself decoupled microservices. And the interface between the management service and the deploy service is an SQS message. So when the user registers an event in our user interface and it is processed by API Gateway and the Lambda, and it's validated, then the create event Lambda here should send a message to the SQS queue that should trigger the deployment. So let's take a look at how SQS and step functions are used to actually trigger the code build deployment. Now, one important aspect in the CDK and CloudFormation is that only one operation can take place at a stack at the same time. So we need some sort of mechanism that allows us to queue the same operations or operations on the same stack while allowing operations on multiple stacks to be executed in parallel. And this can be achieved through an SQS FIFO queue. FIFO queues are based on something called group IDs. And all the messages placed on the queue with the same group ID are guaranteed to be processed in order. And every stack we deploy has its own unique name. So this stack name is actually a very good candidate for the group name. And by using the stack name as the group ID, you can see that messages on that group ID will be processed in order. So the messages number 2 in this diagram will only be processed when message number 1 has finished processing. But the two groups will be processed in parallel, which will lead to parallel deployments to your CloudFormation stacks, which is exactly what we want to see. So the final part in the puzzle is how to trigger this state machine from the SQS queue. Because the SQS queue is a pull or pull-based mechanism, while the step function state machine is a push-based mechanism. So we need some sort of glue to connect the two. And that glue is a Lambda function with an event source mapping. The event source mapping will continuously pull the group, the queue and every group in it. And when any new message is found, it will trigger the Lambda function. The Lambda function simply forwards the exact SQS message to the state machine. And then the state machine will do some additional processing and then run code build. If everything is successful, every step in the state machine, then the state machine will delete the message from the queue. And that will allow the next message on the queue to be picked up and the next deployment on this stack to take place. If any issues occur during the execution of the state machine in any step, then the state machine will set the visibility timeout of the message to 0, return it to the queue, and that will automatically allow this deployment to be retried. And that's the entire flow. So to recap, first the user registers an event, the event that they want to deploy on our event bridge. That is processed by the management UI and the management service, which are pretty standard implementations of a user interface and an API gateway. That will send an SQS message to the deploy service, which will trigger the step functions workflow. That will trigger the code build container, and that will deploy the components using the CDK. And this results in standalone stacks in CloudFormation with unique resources per stack. And those integrate with the shared API gateway and shared event bridge in our core module. And the entire process from a user registering a new event to those components being deployed takes about 3 minutes. And of course, updates to those tags are even faster. And that's how we achieved user-driven composable infrastructure with the CDK at PostNL. Thank you for your attention and enjoy the rest of the day.